Hello everyone. In this video, we will talk about data hazards problem for pipeline processor. In our last video, the first video of week 9, we have introduced the basic idea of pipeline processor. And then we also talked about the speed up for pipeline processor. So how to calculate the speed up of a pipeline processor is really important. It's really important. I hope everyone could understand that part. So I will post announcement. I actually posted that in the Teams page already. So if any of you have not joined the Teams page for this class, you might really want to join that. It's a good tool to use, and then we could discuss questions. We will hold our office hour there. We already did, and we could have like a lot of different features in using Teams. You can chat with someone, you can do a video conference with someone, you can record the video conference, you can post a question there, and you can get answer from me or from the LAs. So be active in the Teams page. You can not only can discuss with me, you can discuss with the other classmates as well. Also, if you want to know anything about the course schedule or not clear, if any of my announcement was not clear, so you want to clarify anything, then you can always post a question to Teams page. So we have a class created in the Teams page for whoever has not joined that yet. Please join that. Please join the Teams page. And also I posted an announcement for the midterm plan. So some of you ask me what is the plan for midterm. So I was trying to get as far as I can, and then was thinking to give you some midterm midterm paper to work on. It's not writing a paper, it's problems. It's kind of like a take-home exam. But I think I'm now able to get that done this week. So I will postpone the midterm to after spring break. So the good thing is you will have a good spring break without midterm to worry. But after spring break, you still need to work on that. So I will give you a take-home exam. Of course, open everything, and then I will give you, I think, at least a week, to finish the problems. And you can always discuss in the Teams page. Send your question. The LA and me will help to answer that in that page. And also, I will probably hold record lecture video focusing on the midterm, so I can go through more questions of your take-home exam and give you explanations and try to work on them, pick a few of them and try to explain them. So, but you don't need to worry about that. So I'll give you like a pretty long time to get that done. So even if it is a exam, it is a take-home exam, but I will give you a pretty long time. So it's not like I send out the exam today and ask you to submit by the end of today. No, I will give you some longer time. I'm planning to do a week, but it could be even longer than that. So, so that's the plan for the midterm. All right, so let's look at the data path. We have introduced the data path of the processor, and we also introduced the pipeline, the basic idea of pipeline. So this is a really important technique for modern computer, and it is almost used everywhere for any modern computer. So we have introduced the pipeline concept, and also we have talked about how to calculate the speed up for a pipeline processor. for a pipeline processor, right? So the example in the slides, we would add 10 instructions in the previous pipeline example, and then so that actually means, so if you still remember, so we were talking about using a particular processor example. Suppose a single cycle processor need 800 PS to implement one instruction. So every instruction costs you 800 PS. And if you have 3 instructions, that will be 800 times 3. If you have 10 instructions, it will be 800 times 10, right? So you can have a lot of instructions. And if you have a pipeline processor, then you need to stack everything together. You need to stack everything together. And by stacking everything together, of course, you are saving a lot of time because you're doing parallel work, parallel tasks at the same time. However, the longest, when you stack the different in instruction, when you stack different instructions together, then you have to have to waste a little bit time if you have like 200 PS for one stage and 100 PS for another stage. So you do have some longer stage, you do have some shorter stage. So this is a longer stage, this is a shorter stage. But when you stack them together, then you have to use the longest stage. You have to use the longest stage, right? If you don't do that, it will be super complex to control. Of course, you can stack whichever way you want, but it will be super complex to control. And later on, when we explain the data hazard, then you will see the reason. So there's a lot of things we should consider about pipeline. And one biggest issue is data hazard. So we will introduce data hazards today in this video. But before that, I want to give you a quick review and emphasize the pipeline speed up again. So what is the pipeline speed up? The pipeline speed up is calculating how much we could achieve using a pipeline processor compared with not using pipeline technique, right? So if you have your original processor and you of course know the execution time, you of course will know the execution time for a way to implement a full instruction, for a way to implement a full instruction. And also we could know if the overall time we need to implement the pipeline version of the original instructions, right? And then we look at the two different versions. When we look at the two different versions, so the first one requires 800, the original one requires 800 times the number of instructions. So this is our overall time. And then the shorter version is actually using the last time period. The last whole time period is still 800 PS, 800 PS. Plus, depends on how many instructions you have. If you have 3 instructions, then you need 2 additional 200. If you have 10 instructions, then you will need 10 minus 1. 10 minus 1. So this is like the IC minus 1. IC minus 1 times 200 times 200, right? And for us to calculate the speed up of the pipeline processor, then we simply need to do the longer time divided by the shorter time. And when the IC number become bigger and bigger, if you are thinking about a real application, then the IC number is actually really big. So usually you have millions of instructions. So this number will eventually become 800 divided by 200. So what is the 800 divided by 200? So the 200, so for the previous example, the 200 PS is actually called the time between instructions for a pipelined version, processor. Okay, so the 200 here is actually the time between two instructions, the time between two instructions for a pipeline processor. And the 800 is actually uh, the, the, the non-pipelined version. The time we need to execute So the time we need to execute one full instruction using a non-pipelined version, right? So then if we understand how to calculate this, then suppose we know the time between the instructions, between two instructions for a pipelined processor. Suppose we know the number of that, and then we will be able to calculate the speed up. We'll be able to calculate the speed up. And ideally, what is this number? What is the time between two instructions? What is the time between two instructions? If you stack multiple instructions together, suppose you have 4 stages, then it will look like this, right? Dot, 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 dot. And then suppose you have 4 stages. Suppose you have 4 stages, and the time between two instructions, of course, will, so if this is in time 0, then this is time 1, this is time 2, this is time 3. So when I start to execute the first instruction, and then I'm curious about instruction number 1, instruction number 2, instruction number 3, how much time should I cost? And this could last for like longer, so you could have many more instructions. And between each two instruction, of course, it will just cost me one stage, right? So the length, the time we actually need, the time between two instructions for a stacked version for a pipeline processor is actually the one stage length. So I have to say this is actually one stage. However, for the previous example, because we have the different stage with different lengths, right? And one stage here, the longest time could be 200 PS, and overall I need 800 PS for the full instruction. So ideally, if you have 5 stage, then one stage can be as small as 800 divided by 5. But this is an ideal case, right? This is an ideal case, which is actually not happening here. So if you have 5 stages, then one stage ideally could be as small as this. However, because you don't have equal length for each stage, because you don't have the equal time for each stage. So the ideal case, for example, this one I draw here. So ideally then, so I have to write this. Ideally then, the length between the time between two instructions when you do a pipeline processor, and it will be, of course, the full instruction time, divided by the number of stages. So if you have 4 stages, and then each one will be 200 PS. If you have 4 stages, each one will be 200 PS. So this is the ideal case, right? So if suppose we have an ideal pipeline processor, then of course the overall speed up will be the 800 divided by, so this is the non-pipelined time divided by one stage length, the length of one stage. So what does that mean? Then this will become the number of stages, how many stages you have, right? All right, so this is really important. Have to draw 5-star again. And then the question so there could be a lot of simple question asked to you. So for example, if I want to have a really efficient pipeline processor, what can I do? So you want to have as many stages as you can, right? So increase the number of the stage. Will, of course, give you a more efficient pipeline processor. So overall, for pipeline processor, the technical pipelining, um, why we could do it. So remember, we're using MIPS processor, and all the instructions they're with the same length, right? If you have some instruction pretty short time and some instruction has to take a longer time, it will be more complex for us, for sure. So we only have a few different instruction formats. Suppose you have super complex instruction set, you have a lot of different types of instruction, this will be complex as well. So the memory operands only appear in the loads and the store. So you only use load and store to communicate with the memory, right? So the longest instruction is the load instruction. So the most time consuming operation is load. Suppose you have a lot of different types of instruction, communicate with the memory. Of course, that will be troublesome. So what makes it hard? That will be, most interesting to answer. So what does that mean? If we would like to implement pipelining technique, um, I don't know how many of you, when you watch the previous video, if you have thought about this question. So is there any limit or constraints you could not do pipeline, or does that affect anything if you stack all the instruction together? If you perform different things at the same time, will there be a problem? Remember, we're not actually doing the laundry. And if you are doing the laundry, so that's this example, right? If you are doing the laundry, then this is super easy parallel problem. Means it's easy to be parallel. It is easy to be parallel because you wash your clothes, your first load, your second load, your third load, you never have an issue. Use your first load and wash it again. And suppose you want to wash something and you put it back into your closet, and later on you want to wash it again. So then before you put it in the closet, you will not be able to wash it again, right? So you have to wait until you get it from the closet, or either a way I can rewash it in an early time. If your current closet is in the dryer, can I take it out to put it in the washer? So because there's no relationship between your first load, second load, between each two loads, there's no direct relationship with them. So of course you can do things in parallel, right? And this is also the basic idea why GPU graphic card can be so efficient, because you can handle a lot of data, and the data they need to be calculated at the same time, and they're not related with each other. With each other. So, however, in our example, suppose we're doing the instruction stacking, right? So we're pipelining the instruction. If you do the instruction, then of course you're calculating different things. And usually we will have, in the C program, for example, we have x equals x plus y, y equals x minus y. So you have a lot of connection or relationship dependencies between different or among all the different instructions and your calculations. So just like this example, suppose I have a load. So suppose I calculate a subtraction, and then my result will be put in $T2, and later on I want to calculate AND using $T2 as an input, and later on I want to calculate OR using $T2 as an input. So if you keep using $T2, if you keep using $2, then your $2 is actually generated by the first instruction and used as an input by the second instruction. How can that happen? So if you want to wait until the end of the first instruction, of course, there will be no problem. However, we're talking about doing things in parallel. So we want to calculate the $T2, generate the new value of $T2 using the first instruction, and at the same time, we also want to use it as the input of the second instruction. This will, of course, cause some problem because your result was not generated when you start your second step, right? So if when you start to calculate your second instruction, the input of the second instruction was not generated yet. The input of the second instruction was not generated yet. So this is a really big problem. So this is one big problem we will introduce today. So that's called data hazards. That's called data hazard. And what is structure hazard? What is control hazard? So then you get like a basic idea about hazard. So the hazard means you do have a conflict, right? You do have a conflict. Hazards means kind of like means you do have a conflict. So you have to solve certain conflict. So structure hazards means suppose we had only one memory. What does that mean by only one memory? So we do have one memory, we have the whole RAM, right? So the RAM, we have the main memory, we have remember, we have the data segment, we have the text segment, right? We have static data, dynamic data. Suppose I mark everything, this is the data segment, and this is the text segment. So we do have two pieces of separate memory. We do have two pieces of separate memory. So this is the memory for the program, and this is the memory for the data. So we have two pieces of memories for MIPS. For MIPS processor. So MIPS processor will solve this problem. So we will never have a structure hazard. We will never have structure hazard. But suppose you're using one particular processor, which is not MIPS processor, and you only have one memory. So your program and data, they're stored in one whole piece of memory. Then of course, if you want to read the program and read the data at the same time, and you're reading different things using one piece of memory, and you're keeping so like your input output of that piece of memory will be super hard to control, right? So if you want to do things in parallel, then of course the more device you have, the better. The more devices you have, the easier it will be. Right? Because you don't want to read things from one location at the same time. You don't want to write things to one location at the same time. And if you are doing things in parallel, of course, you are reading and writing different things, writing and writing. So you're reading and writing different things in the same time. So what is control hazard? Branching instructions. Need to worry about branching instructions. So we will talk about control hazard in next video, next week. However, I will give you a heads up right now. So sometimes you need to worry, well, my result of the next calculation has not been generated yet. And sometimes you might want to worry, if I want to jump to certain location, if you still remember, so we did a lot of assembly code, right? So we have all different types of branching instruction. According to certain condition, we might do a branch. And if we want to do things in parallel, that means you want to move some things in advance. So you want to calculate different things in advance. And if you do things in advance, what will happen? Then you have to know the result of certain things, right? So if you want to make a branch, you want to jump to somewhere according to certain conditions result, and then it will be a big problem that how about it if you jump, if you not jump, right? So if the branch was taken, if the branch was not taken, so it will be different situation. For the different situation, then what should we do to do the parallel processing? What we should do, right? So that will be a big question we could think about. Actually, we don't have a video in next week. So we have spring break next week. So you can think about this question over the spring break. So this is actually what I draw in the previous video. So I actually highlight or separate the whole data path of the processor into a few different steps. And what's happening actually in reality, you do have registers. registers, like this kind of register. So they're all like registers. You could view them as some temporary storage inside of your CPU. You do need to keep the data from this part and put it here, and keep the data from this part, put it here, keep the data from your ALU output and put it here, and then take it, so each key element, each important piece of the processor of the CPU here are responsible for different types of operation. And then after one type of calculation or one type of operation was done, then the data has to be kept somewhere. The data has to be kept somewhere, right? So that's why we actually have some registers, like this kind of huge register to temporarily hold the value, But we don't want to focus on circuit structure, as this is in your 1400, should be in your 1400. So I will skip this one. And then let's look at if I want to graphically represent the whole CPU, and with a much nicer way compared with this, right? This is super complex. So how it will look like? Suppose we write the IM block as, we draw a small IM block as the instruction memory, and then the REG is the register file. ALU is the we all know the previous ALU, arithmetic logic unit. So DM is the data memory. And the REG here, they're the same thing. Okay, so those two are the same thing. So the REG here, they both of them refers to the register file. So why we want to put another REG here? Because we know after the last step of your load, the last two steps of your load is reading a piece of data from the data memory, and then you need to send it back to the register. So if for me to better analyze the pipeline processor, then we want to draw the register here again. But we only have one register file. Okay, so it's only physically only one register file, and the graphically representation, you could have two register file, but they refers to the same thing. All right, so in this figure, then it will be easier for us to understand what's going on. So suppose we're performing a load, so how the data was transformed from one part to the other part, how the data was transmitted from one part to the another part. Initially, we need to take a piece of instruction from the IM, and then the instruction need to be used to decode which register we want to use, right? So the CU will decode the IM, will decode the instruction, and then we will need to read. Certain register out. From the register file, and then the input of the register will be used as the input of the ALU, and then the ALU calculates the result and use it as an address to the data memory. And then after we got the piece of data from data memory, then we can send it back to the register file. So the last step here, CC5, so the CC means the clock cycle. So the CC5 here means I need to put a piece of data into the register file. And the CC2 here is actually taking a piece of data from the register file, one piece of data from the register file. So you know why we have the different color for one piece of for example, if this hardware, so this is the register file, and the first half here means red, and the second half here means read. Sorry, the first half here means read, the second half here means read. Okay, so and later you will see the great usage of that. And why there is one more line here? So that line actually will be used. So the data could be transmitted through that line. For example, suppose we're doing ADD. So if we're doing ADD, then we do not need to read anything from the data memory, right? So suppose I'm doing ADD, and then I will have use a blue line to indicate how the data paths look like. So we first need to still take a piece of instruction from the IAM, and then we need to read the data from register file, and you will have two input go through the ALU, and then you need to use ALU to add them together, and you will need to go to send the result to the register file. So we don't even need to go through the data memory. So there is a bypass. For the data memory here. All right. So let's look at if we're using this kind of graphic to represent the pipeline processor, and then how can we do pipeline for different instructions, right? So this is a pipeline for LW. So you have 3 LWs, and you simply perform load all the time. And if you're doing same job, and then you can, of course, easily stack them. And then your data, they have nothing related with each other. So you keep doing the simple job. However, in reality, this will not happen. Because, for example, if we deal with subtraction, addition, or AND, so we have like this kind of general arithmetic logic calculation. So suppose we would like to do pipeline. And then what will happen? So this is a really interesting example. And as I told you, so we use the color, we use the highlight the different part of the register file of the memory, data memory. And so it actually means the first half actually means we are performing a write, and the second half actually means we're performing a read. So why we want to do that? Because we assume then the read can be finished in the first half of that clock cycle, and the read could be finished in the first half of a clock cycle. In the second half, the read can be finished in the second half of a clock cycle. And this will be interesting. This will be important because if you are reading and writing to the same location, then you could actually get that done in one clock cycle, right? If you're reading and writing to the same location, then you could actually get that done in one clock cycle. All right, so then let's look at this particular example. Suppose we would like to perform subtraction. The subtraction result will be put into $2, and then we want to use $2 as an input of the AND, and then we want to use $2 as the input of the OR, and then we want to use $2 again for the input as ADD, and then we want to do store again using $2. So this particular example tells you sometimes you could have great data dependency, right? So you'll keep using the same register, and we call this kind of dependency as data dependency. So simply you could view it as, well, the data are related with each other. So you have to have the data generated before you use it, right? So for us to get the result of the first subtraction, so the first subtraction instruction has to go through stage 1, 2, 3, 4, 5 to get everything done, right? Because this is taking an instruction, decode the instruction, use ALU to calculate subtraction. You don't need to use the data memory, but you need to put the result into the register file, so which costs you 5 clock cycles. And then suppose I want to do AND, using the $2 as my input. So ideally, I want to stack the second instruction immediately after the first instruction. So then from C2, from clock cycle 2, I would like to get the first stage of the second instruction done, right? However, this will cause a problem because in my second stage of the second instruction, I will need my $2 ready. So I assume $2 is there if I want to do this, right? However, $2 is of course not updated yet, right? So $2 is not updated yet. $2 is not updated yet. So that is a big problem. That is a big problem. And if you just stack them like this, you of course will cause problem. And how about the third instruction? If you do OR and you will need $2 get ready at the second stage, of the third instruction, which is CC4. But by CC4, of course, $2 is not updated yet. Of course, $2 is not updated yet. So same, so on and so forth. So by the fifth instruction, then you don't really have any problem. And on the fourth instruction, you could actually do that because even you're reading and writing from the same location, however, you could get the reading and the writing separate in the first half and second half of that clock cycle. So there won't be any problem for this one. However, there will be problem for the second one and the third one. So how can we solve this problem? So this is called data hazards. The data hazards occur when the pipeline must be stalled because one step must wait for another to complete. So there are some different things sometimes we can, if I cannot solve this, then I'll have to, wait, right? I have to wait. However, if you look at this particular example, so we are first performing subtraction. And then we're performing so we're first performing subtraction, and then we're performing a and logic calculation using the result of the subtraction. So if I don't want to wait, to the last step of the subtraction, is there a way I can calculate? A and D? Is there a way I can calculate my second instruction? So the answer is yes. So what we are doing currently right now for this particular example is we are trying to calculate $2. We're trying to generate $2, and then we're using $2 as an input. However, when is the result for $2 ready to use? So we are adding $1 by $3. But this process is actually done by the ALU. So it is performed inside of the ALU. And then when the ALU finish the calculation, then you should have $1 plus $3 already there. You should have $1 plus $3, $1 subtract $3. We should have $1 subtract $3 ready for us to use. Right? Immediately after ALU finish the calculation. So we don't even need to put it back to the register as long as I get this number. And what we need to do for my second instruction is taking that number, which is $1 minus $3, and use it to add $5. Of course, I need to I need to have $5 from the register file. And the other input of my ALU, here could actually just come from $1 minus $3. Could actually just come from $1 minus $3. So that means you don't even need to send the result back to the register, and you can directly pass it to ALU. You can directly pass it to ALU, right? So why I want to put it in a register and then take it out from the register again? So I don't want to put the result to the register and take it out again. So it makes no sense for me to do that, right? So if I know what I'm looking for, then I can directly pass this number to the ALU again. So after the ALU generated the $1 minus $3, and then you just need to give it back to yourself and then calculate as you use it as an input. Use it as an input, right? So we call this as forwarding or bypassing. Forwarding or bypassing. Okay, so there's a term called forwarding or bypassing. This is really important. Forwarding or bypassing. Okay, so the AND here means the AND calculation. So for this example, as soon as the ALU corrects the result for the subtraction from the subtraction, then we can pass it, bypass or forward it to the as the input to ALU again, and to perform the AND, right? And how it will look like? It will look like this. So suppose you are calculating one instruction, and then your result is the same as the input. So your first instruction's result is same as the second instruction, input. Right? And what we can do, because we know the result is actually generated by the ALU, and we just need to have one secret communication. So it's kind of like a secret communication, right? So pass the result from the ALU calculation to the ALU input, And what is that called? It is called forwarding. Or bypassing. So the forwarding here, if I call it a secret communication, so you have to have a secret channel. You have to have something to pass the data. And in the circuit, of course, you will have to have this kind of connection in your circuit. So that means this actually changed the original structure of the CPU, because you add some more connection there. Right? So how to implement this? The circuit will look like this. Remember, this is the initial figure of the CPU, right? So the blue line here represents how you change the circuit. So this is not required, but I think it's pretty interesting. So for this class, Compare 2, we are not requiring the detailed circuit structure. So I would say not required. However, I put this couple page here just for whoever have the interest to look at how you can implement this. And if you have questions about this, you can always discuss with me. All right, so, and there will be another question. How about if you are doing first the load and then subtraction? So the load need to read a piece of data and put it into $S0. So $S0 serve as kind of like the result you generate from load, right? Even it's not calculated using ALU, it's like a piece of data, but it is the result of the load. However, where the data come from? It comes from a memory location. So suppose your next instruction is a general ALU calculation, such as subtraction. So you want to use your S0, as the input to the second instruction here, Can you do the forwarding? Of course, no. What's the reason here? Because the result was not generated by the ALU. the result is not generated by the ALU. The result is actually inside of the memory, and you are not able to go to the memory. You are not able to go to the memory, right? So if I want to make a connection, so I know I need to have my $S0 ready, and I want to connect something to my ALU in the second cycle here, the second instruction, for the second instruction. However, the $S0 is not ready until the last step, until the fifth stage in the first instruction. So this part is a little bit confusing, hard to understand, okay? So if you have any question, please don't hesitate to ask me. So you can always post your question, but so you really need to understand this. So the the first instruction is a load, and then the $S0 will be only ready after you finish the whole instruction, which is the fifth clock stage, which is the fifth stage here, right? So we're not able to get $S0 ready until the fifth stage. So how can we solve this problem? Of course, I do not want to wait until the fifth clock stage, right? But I could actually save a little bit time, because the $S0, the value I want to read, So suppose it's an apple. Suppose I call it an apple. So the apple is somewhere inside of the memory, And I have to take that apple out. And one thing I can save is I don't need to put it back to the register. right? So I don't need to put it back to register, because I do need the apple as the input to my calculation. However, I cannot forward this apple to an earlier time, right? So I cannot forward this apple to an earlier time. If I connect the data memory to the input of the ALU, and then what you are doing is you assume you can take this data to wherever you can. Of course, this is not read. Because you have to wait until this timeline to do any forwarding, right? So before you read it out from the memory, how can you move it? Right? So before you read it out from the memory, there's no way for you to move the data. So you have to take the data out and then move it somewhere. So of course you cannot forward to an earlier time. So that's why we have to draw it in a time frame. So what we could do? Well, that means I have to wait a little bit. And we call this as pipeline stop. So we have to wait a little bit until we can take the data out from the memory. And then if the data is ready by 800 PS, and then I can move it to the input after 800 PS, right? So if you have to move a little bit and you have to shift one stage, to the right by one stage. So you have to shift to the right by one stage, right? So this is kind of like waiting by one stage to start your next instruction. Another way to call this is adding some bubbles into the pipeline. And what it is actually doing, the CPU just do some NOP instruction. So it's kind of like doing nothing, only waiting there. But you don't need to wait a long time. You just need, for this particular example, just need to wait 200 PS, right? 200 PS, which is not really bad, which is not really bad. So we call this as pipeline stall, which is really important. So to summarize what we did today, so we have introduced two types of solution, two different solutions to handle. So two different solutions to handle the data hazard, right? One is, of course, if we can do forwarding, then we will do forwarding. And sometimes we cannot do forwarding because of the troublesome instruction load, which has the longest time needed, right? So the result can only get ready at a really late time. So when you have a load, and we want to use it for a general arithmetic or logic calculation in the next step. So the combination will be load plus ALU. So the previous instruction is a load instruction and the next instruction is an ALU instruction. If you have this kind of instruction next to each other, and then what we have to do is pipeline stall. So we have to stall one clock cycle. We have to stall one clock cycle of the pipeline to solve this problem, right? So when you stall one clock cycle, you are still doing forwarding. But we have to stall one clock cycle. All right, so that's the lecture today. And have a nice spring break. I will see you all after spring break.